Hi, how's it going? So there's more calculus today. Yes, calculus. Yes. Implicit differentiation is what we're going to look at. Okay, what is implicit differentiation? What do we mean by it? Well, this is what's called an implicit expression. Okay, why is it called implicit? Because it's in terms of x and y, but more specifically, it's a bit difficult to make y the subject. Okay, and that's what implicit differentiation is all about. When it's either difficult or impossible to make y the subject. If y is a subject, great. You just find dy dx as you have learned already previously. But when you've got something like this, you've got a y cubed term there and a 3y term there, you're not going to be able to make y the subject with that. And so we need to use what's called a method of implicit differentiation. Effectively, what we're doing is we're differentiating both sides of this equation with respect to x. Okay, we're differentiating both sides with respect to x. So let me just write that a little bit differently. We're finding d dx of the left-hand side. I'll write LHS for left-hand side. And we're finding d dx of the right-hand side. And because I'm talking about implicit differentiation now, I'm going to write it in that particular way, okay? You're differentiating both sides, but with respect to x. The dx means with respect to x. So let's just start off and see how far we get. Okay, so we'll differentiate the first term with respect to x. That's easy, 3x squared. So that's fine. And then we'll do the next term. Differentiate x with respect to x. That's easy. You get 1. So 3x squared plus 1. All going okay so far. But then you get to the next term, y cubed, and really you'd want to differentiate with respect to y. But we can't. We've got to differentiate with respect to x. So we've got to do something a bit different. So I'm going to come back to that. Okay. Let's suppose that y is some function of x. Doesn't matter what it is, but y is some function of x. And let's just suppose, for argument's sake, it's this. It's x cubed plus 2x. Just pretend and go with it for the moment. Okay. Well, finding dy dx is pretty easy, isn't it? Okay. Obviously, dy dx, let's just write down, is going to be 3x squared plus 2. Remember, we can do that because this is an equation where y is the subject. Okay? But we want to find y cubed, so let's see what happens when we cube that. Well, we can cube that, it's quite easy. Okay? We can find out what y cubed is. Okay? It's just this, x cubed plus 2x, all to the power of 3, that's y cubed. And we want to differentiate this with respect to x. Okay? You can do that, you can differentiate with respect to x. Let's just write down what we're doing here. We're finding d dx of y cubed and d dx of this, differentiate with respect to x. We just use the chain rule for that. Yeah, chain rule. So bring the 3 down, so you get 3 times x cubed plus 2x. Decrease the power by 1. Then remember to differentiate what's in the brackets, find the derivative of what's in the brackets. So of course that's going to be 3x squared plus 2. That's our answer. But notice how you can also write it like this. You can write it as 3y squared dy dx. Because that, x cubed plus 2x, is the same as y. And that, 3x squared plus 2, is the same as dy dx. So that is 3y squared dy dx. Now ask yourself this question. If I chose y to be a different function of x, would you still get the same answer? As in, would you still get 3y squared dy dx? Well, yes, you would. If you don't believe me, pause the video and try it. You write down any function you want there in terms of x, and you're going to get 3y squared dy dx. Because you're always going to end up cubing this, because we're doing y cubed, don't forget, you're going to cube this, and don't use the chain rule. So just, if I ignore the brackets a moment, if I just erase what's in the brackets, you've got something cubed. You're always going to have 3 times that something to the power of 2, okay? And remember that function of x could be anything you want, okay? So you end up with 3 times the function of x squared times by f dash x. Or let me just write it up a slightly different way than what I've written down here. When you differentiate that, okay, when you do d dx of y cubed, I can write it in brackets or like this, let's just put it in brackets again, okay? You're going to get 3 times f of x to the power of 2 multiplied by, bracket, lots of brackets, multiplied by f dash x. Okay? Yeah. And then we can make a generalisation from that. Okay? Well, let's just do it as y to the power of n. Let's do a generalisation. I'll write it in by here so you can see everything, okay? If you want to differentiate d dx of y to the power of n, what are you going to get? You're going to get n y to the n minus 1 times by dy dx. All I'll do is just change that power, you see. If I had power 4, say, I'll bring the 4 down, then I have f of x cubed, and then times by f dash x. If that power was to 10, say, I'd have 10 f of x to the power of 9 times f dash x. Okay, so the general result is when you're differentiating y to the power of n, you'll get n y to the n minus 1 dy dx. Okay, and that's a really handy result that you probably ought to write down somewhere in your notes. Okay, so let's go ahead and continue to work through this. So when we differentiate y cubed, we know the answer now then. It's going to be 3y squared dy dx. Okay, using that general result we had earlier. And then when we come to the 3y, well, the 3 is just a coefficient, so just keep that there, and then differentiate y. Well, using the similar rule, okay, if it's y to the power of 1, you'll get 1 y to the power of 0, y to the power of 0 being 1, times dy dx, it's just going to be dy dx. Which, if you think about it, is obvious. Come back to this, when we had y on the left, differentiate that with respect to x, we get dy dx. Okay? And then equals 6, so just continue on, you get equals 0. Okay? If I just rub this off, you can see here, that's our expression once we differentiated both sides. Okay? And that is pretty much it. Okay? When it says find dy dx in terms of x and y, what it means is make dy dx the subject now. Okay? So once we've done the differentiation, we need to make dy dx the subject. So on the left hand side, let's just put it up here. On the left hand side, the thing to do is normally factorise. So you've got dy dx, find all the dy dx terms. So you've got 3y squared, okay, plus 3. And then put all the non-dy dx terms onto the other side. So 3x plus 1. And I'm going to write that as negative of 3x plus 1, like that. And then you can see, to make dy dx a subject, you're going to have dy dx is equal to negative, and then it's 3x plus 1 all over 3y squared plus 3. And notice you will get an expression in terms of x and y because of the very nature of the question. So that's it. That's implicit differentiation. Okay, I'm hoping that made a lot of sense to you. There's another example coming right up. So here's my second example then, involving implicit differentiation. So find the equation of the normal at a particular point, the point 2,1, to the curve of the equation, y squared plus 3xy is equal to 2x squared minus 1. So notice again the need for implicit differentiation. So in our equation here, we've got y squared and we've got y, and we're not in a position to make y the subject there. Okay. It says leave your answer in this form. All right, so let's go ahead and do that. So what we do is we differentiate both sides with respect to x. Okay. So when we differentiate y squared, what are you going to get? You get this, 2y dy dx. Now, let's just talk about a quick way of memorising this. Okay. So before I talked about in terms of what happens when y is a function of x and y gets a result, but let's just think about how simple to remember this. Okay. All you do is just think of it this way, differentiate as you would do normally. When I say normally, if you differentiate x squared, you get 2x. So just think about what you get when you differentiate normally, so 2y, but then because it's y, just put a dy dx on the end. That's what we do. So differentiate under normal rules to get 2y, then just put the dy dx on the end. Okay, and that's how it's going to work. And then this one, right, what we have to do here, this, you have to use the product rule. Okay, remember that? Because you've got the product of two things, you've got 3x and y, so you have to use the product rule. Okay, so the product rule, remember, just have one of the terms being 3x and the other one, v, is going to be y. And then you write down what each one is. I'm just writing down some work in just in case you need a quick recap of how the product rule works. So that's going to be 3 and then dv dx. What do we get when we differentiate that? You get dy dx. Okay. Effectively, it's 1 times dy dx, isn't it? So dy dx. And then the product rule is v du dx plus u dv dx. Okay, so I think we can write that down now. Let's just put that over there. So plus v du dx is the product rule, so 3y plus u dv dx, 3x dy dx. Some of you might have been able to just write that down without the working, in which case that's fine. All right. And then equals, and then differentiate that with respect to x, so that's going to be 4x, and that's just going to be 0, isn't it? Okay. So we've got that. Okay. Do we need to rearrange it? Do we need to make dy dx a subject? That's the question I'm asking you. No, we don't. We don't have to. Okay. Because we're given the points to substitute in. Remember, this is a question about finding a gradient now to enable us to find the equation of a normal to a curve. And if we've got the points to substitute in, there's no sense in rearranging straight away. Okay, just substitute the points in. So what I'll do is I'll write at the point 2, 1. Now remember that means x is 2 and y is 1. So when you've got an expression in terms of x and y, you've got to substitute both of these coordinate points in. Okay, so 2y, so it's going to be 2 times 1, so that's going to be 2 dy dx added to 3y, so 3 times 1, so added to 3, and then added to 3x dy dx, so it's 3 times 2, so that's 6 dy dx, and then that's equal to 4x, so it's equal to 4 times 2, it's equal to 8. Okay. You do need to find what the gradient is, so you do need to find dy dx, but what I'm saying is it's now going to be easier to find dy dx when the numbers are in. What I'm saying is it's a bit harder to rearrange and make dy dx a subject when it's all in terms of variables, but when it's in terms of numbers it's easier. So that's why suggestion is substitute that point in first and then rearrange again. So that's pretty easy. So you've got 2 dy dx plus 6 dy dx, so that's 8 dy dx, and then if you put the 3 into the other side, that's equal to 5, and then just divide. You have dy dx is equal to 5 over 8. Okay, and that's what dy dx is. And then let's read the rest of the question again. So find the equation of the normal. So I'm going to underline the word normal here. So that would be the gradient for the tangent, wouldn't it? Dy dx. So I'll just write down for the normal, we want m, our gradient to be negative 8 over 5. Just take the reciprocal and multiply by negative 1. Okay. And then we're ready to go. Then we're ready to write down the equation of the normal. So let me just get rid of this now. Notice how much space I need, which is why I'm doing it with my large board in the classroom today. Okay, because I need all of this space. So y, let's just remind ourselves, y minus y1 equals mx minus x1. That's the equation I'm using, you see. And so y subtract the y coordinate, which is 1, equals the gradient, that negative 8 over 5 times by x minus x1, which is 2. Okay. And that would be fine as our answer. Only, of course, it says give it in this form here. So what I would do is I'd multiply both sides by 5 first, so there's no fractions involved. So multiply by 5, you get 5y minus 5 on the left, and on the right, you've got negative 8. Let's expand the brackets as well while we're at it. So negative 8 times x, and then negative 8 times negative 2, so plus 16. And then I think we're ready to write everything in that form. So let's put that over to the left-hand side. So you have 8x plus 5y, and then we'll subtract 16 as well. So it'll be 5, subtract 21 is equal to 0. So 8x plus 5y minus 21 is equal to 0, and that's our equation of the normal. Okay. I'm hoping that you found it helpful, found that useful. Okay. I'll see you again.